In this video we're going to look at the direct distance law of motion. So instead of looking at the force as inversely proportional to the distance to some point squared, we're looking at the force as directly proportional to r. So we can say that the force is equal to mu(r). So from conservation of energy we can say that the potential energy plus the kinetic energy is a constant. And we can also say that the stationary action is going to be given by this here, which we've seen in our previous video. So it's going to be twice the integral of the kinetic energy with respect to time. So we can say that 2 times, so the kinetic energy is half mv squared by dt, so the 2 cancel with a half. We can take the m out, so we get our m times the integral of v squared dt. Now our v squared, it's instantaneous velocity, so that's the instantaneous displacement ds, or tiny displacement ds with respect to our time dt. So therefore we can say that the v dt is equal to our ds. So we can put this here into this little equation, and again we get the m times the integral of v ds equals the value of I, and this is a thing that's stationary. So but we have to go now and find out what the v is and what the ds is. Now one part of the v we can find from the kinetic energy, which is half mv squared, but the potential energy this time is slightly different. The potential energy this time is going to be, the limits are going to be from 0 to r. So you can see that because if you had like in the previous example, if the limits were from r to infinity, then we would have an infinity for this value of r. The whole thing would tend off to infinity. It wouldn't make any sense. So the limits are from 0 to r. So whenever we integrate this mu(r) by dr, is simply going to give us a half mu(r) squared. So this thing here is going to be our potential energy. So let's continue like this, the same as we did in the previous video. So we can say that our total energy here is going to be the kinetic energy plus the potential energy, and that's going to be a constant. So we'll have a half mv squared plus a half mu(r) squared is equal to a constant. So we can call the constant k. We can take the 2 up to the other side, so we'll have a 2k. We'll make the m equal 1, and then we can take over the factor of that's left, which is the mu(r) squared, over to the other side. So you get that v squared equals 2k minus mu(r) squared. So we can see that v squared is equal to, if we take the value of mu out, it gives us 2k upon mu minus r squared. Now we'll give this term 2k upon mu a one term, we'll call it a squared. Okay, we call it a squared as opposed to a just because it helps the maths work out a little bit better and a bit easier. So this gives us then, if we were to take the square root of both sides, it would be the square root of the mu, and it would be the a squared minus r squared to the power of a half. So that's the value of v we're looking for, and the value for ds is exactly the same as in the previous video. It's going to be our 1 plus r squared theta derivative squared to the power of a half. So if you're unsure of that, you can have a look at the previous video, but we've seen this a couple of times. In fact, this is the third time we've seen this one in all of our examples. So therefore we can say that the functional is going to be of the form I equals mu(r) from some point a, b of a squared minus r squared to the power of a half times 1 plus r squared theta derivative squared to the power of r by dr. So we can simplify it if we just let the value mu equal a value of 1. So we can see here that we have a functional, and the independent variable is the r, and the only other part of this that's got a dependence on r is the theta derivative. So again, we can use a simplified Euler-Lagrange, and we can write that out as partial f by partial theta derivative equals a constant. So all we've got to do is then differentiate this thing here with respect to theta derivative. Now the only thing that's got a theta derivative in it is this term here, so that will just be left as the same as it is, and this term here is just going to be the chain rule. So it'll be half of 1 plus r squared theta derivative squared to the minus a half, and then we differentiate what's inside it. So that's going to be the value of 2r theta derivative, and that is equal to a constant. So we'll just call it a constant squared. Again, it just helps the maths when we work through the rest of the example. So the 2 cancels with the half, so we're left with the a squared minus r squared, and in the top line we've got our r theta derivative, and that minus a half can come down to the bottom line, so it's 1 plus the r theta derivative squared to the power of a half equals c squared. Now we want to get rid of these squares root signs, so we can square both sides. So we can square both sides, and then we can take this up to the c squared as well, and we get this line here. And then we can multiply out by our factor of our r to the 4 theta derivative to the 4, and we get this line here. And then finally we can take everything all over to one side, which gives us a value of c to the 4. So c to the 4, and then we can take out our factor of theta derivative from all of these, and we get this term here, c to the 4 equals theta derivative squared into a squared r squared minus r to the 6 minus c to the 4 r to the 2. Now there's just a lot of algebra involved in that, it's just really to get it down into a standard form, so let's continue with that on the next page. So we have our theta derivative squared then is equal to this term here. So therefore we can take the square root of both sides and we'll get a c squared here, and this thing here is going to be the square root of all of this, and we can take out the factor of r to the 6 from here as well. So therefore we can say that the theta derivative is equal to, we can take that r to the 6 out of the square root brackets, becomes r to the 3. So then we can take the integral of d theta is going to be the integral of, well, we just separate these things out, so it's going to be c squared upon r cubed dr, all upon 1 upon all of this to the power of half. Now this is in a standard form. The standard form is the integral of minus 1 upon the square root of a squared minus x squared equals inverse cos x upon a. So again, we can use a substitution. If we say u equals c squared upon r squared, then we work it through until we get our du is equal to minus c squared upon r cubed, which is this term here. So I won't get through all of the algebra but with the integration, so we integrate that up, and when we integrate it using that substitution we get this equation here, c squared upon r squared equals a to the 4 upon 4c squared minus 1 to the half cos theta plus beta plus a squared upon 2c squared. Now the full integrations in a piece of paper in the resources section in a PDF, so you can go down and have a wee look at that. I just didn't want to fill it out because there's just another lot of algebra here. So this here again is the equation of an ellipse, and this is the eccentricities given by this term here. So again, if it's a direct distance law, we'll still get an ellipse, and we'll go and we'll have a look at that in the graphical calculator now. So this is the equation that we've just derived, and I've put it into the graphical calculator. Now the c squared upon r squared has been rewritten as 1 upon c squared, and the whole equation here to the power of minus a half. It's just so as I could get everything in terms simply of r. So this again here, you can see that if we were to adjust the value of beta, it just adjusts to the angle of the ellipse. And if we were to adjust the value of a, it just changes the value of the eccentricity. So it becomes more elliptical or it becomes more circular. And it tends towards a circle, and then it'll disappear when this value here tends to 0. Okay, so you've got access to that in the resources section. I'll leave it down there for you to have a little play with it. So that's all there is for this video. I'll get you on the next video. Goodbye.